Hello everyone, my name is Yun from Shanghai Jiao University. Today I'm going to talk about our recent work on optimizing I/O pass-through in virtualized environment. This project is in collaboration with Alibaba Cloud. Together we propose a software solution that allows pass-through device to work without pinning all the guest memory. So in cloud data center, memory is expensive. To save resource, cloud provider tries to reclaim use or code memory through memory recognition or other techniques. But once a memory use device pass through, reclaiming memory becomes very hard. That's because I/O device, unlike CPUs, cannot handle page fault. If a device tries to access a page that was swapped out, it causes an I/O page fault or IOPF, which may crash the system. Let's take a quick look at the background. In virtualized system, I/O was initially handled by software like VirtIO, but to improve performance, more VMs now use device pass-through. This means VMs talks directly to the device, like a NIC or NVMe, and bypass the hypervisor completely. That brings near-native performance, but also a serious problem. Since the hypervisor isn't in the loop, it has no way to catch page fault triggered by the device DMA. To avoid this risk, current systems simply pin all memory used by the VM, but this wastes a lot of memory, something that cloud provider really cares about. So solutions like address translation service and page request interface were proposed long ago by PCIe SIG, but they require support from hardware, IOMMU, and the OS altogether. In practice, very few platforms support them. Even Intel's newer servers are only just starting to support address translation service. So people have tried to fix this in the other ways. There are some software approach like VIOMMU, which simulates an IOMMU in Qumio to track DMA, but it costs a lot of VM access and slows things down. Other ideas like Core IOMMU and IO Guide involves either guest cooperations or custom driver change, which limit their usability in production. Some vendors use hardware-based solutions like Mellanox NICs with on-demand paging, or Alibaba's VPRI on DPU, but again, this requires special hardware. Then the question is, if we already have so many solutions, including some in production, why do we still need VIO? The answer comes from the reality. We look at a real-world cluster with 300 nodes in Alibaba Cloud. About 80% of the VMs are legacy VM. They have been running for over a year. These older machines don't support address translation service or on new DPU hardware, and all their memory is pinned. In total, that's over 800 gigabytes of memory, and around 270 gigabytes of it is called barely accessed memory. Yet, no existing solution can reclaim it safely. Therefore, we can conclude that most existing solutions only works for newly created VM or those running on the newer hardware, but lack effective support for the large number of legacy VMs that are still dominate in many cloud environments. So we ask, can we handle I/O page fault in software on existing hardware without modifying the guest and with minimum performance impact? That's why we build VIO. It's a software-only solution built on the standard VirtIO interface. VIO is fully transparent to the guest and doesn't rely on any special hardware. It includes 3 key components. First, a mechanism to monitor DMA operation before they happen, so that any missing pages can be detected in advance. Second, a flexible mode switching design, which allows the system to switch between full pass-through and snooping I/O based on the VM's I/O workload. And the third, a lightweight page locking mechanism that pins only the frequently accessed I/O pages to reduce the chance of faults, page faults. These 3 mechanisms are designed to address the key challenge of I/O pass-through without pinning memory. The first challenge is that hypervisor normally cannot see the device DMA active. So we use DMA snooping to proactively detect and resolve potential page fault. The second challenge is performance. Monitor every I/O can introduce overhead. That's why we use elastic mode switching. In low IOPS, a VM stays in the safe snooping mode, while high IOPS VMs can temporarily switch to full pass-through. Finally, to reduce the frequency of fault even further, we use selected page locking, target only the hot I/O page, which avoid unnecessary memory pinning. The first challenge we face comes from the nature of I/O pass-through itself. All I/O operations bypass the hypervisor, leaving it completely unaware and unable to intervene. This is the fundamental reason why memory has to be statically pinned in the first place. So let me explain how we monitor DMA. Normally, in VirtIO, the device and the guest share 2 ring buffers, the descriptor ring and the available ring. The descriptor ring contains the actual I/O request descriptors. That is, metadata about where the buffers are and what operation to perform. The available ring, on the other hand, is where the guest places the indexes of this descriptor to signal new I/O requests to the device. When the guest submits a request, it updates the index in the available ring, and the device sees it and performs DMA. In VIO, we insert a shadow index. When the guest writes to the ring, it only updates its own copy. The device cannot see anything yet, but the hypervisor sees this update and intercepts it. At this point, the hypervisor checks the descriptors and snoops the memory address involved in the DMA. If the page is swapped out, it brings it back. Only after making sure all the pages are resident, the hypervisor updates the shadow index, so the device can continue. This way, we completely avoid DMA-triggered page fault. And since all this happened before the actual I/O, we don't interfere with the device or the guest. Compared to hardware solutions like on-demand paging, which handle faults during DMA and rely on retransmissions to recover, our methods keep things clean and stable. The device never fails in the middle of the DMA transfer. But there is a catch. Even though each snoop is very fast, about 4 microseconds, doing it for every I/O can add up. In benchmark like NetPerf, we found that VIO's peak performance is about 10% lower than the pass-through. That's too much for some users. However, in real production workload, high IOPS VMs are real. Across the full Alibaba cloud platforms, only about 3.6% of VMs have IOPS above 30K. So we introduced elastic pass-through, a dynamic mode switching system. When IOPS is low, we run in snooping mode. When IOPS rise, we switch back to full pass-through. This makes sense because under high I/O pressures, memory usage is already high, and trying to reclaim memory under such high I/O pressure will cause significant performance drops. So it's simply not a good idea. Elastic pass-through also helps us upgrade legacy VM. We can switch a running VM from pass-through mode to snooping mode without rebooting. To support VIO for legacy VMs, we first need to upgrade the Cumul hypervisor in place so that it includes VIO functionalities. This is done using Cumul's live upgrade capability without shutting down or migrating the VM. Once the upgraded hypervisor is in place, we can switch the VM's I/O mode from pass-through to VIO. Specifically, we remap the ring buffers to enable snooping. First, we unmap the available ring from extension page table, EPT, temporarily to block guest I/O submissions. Then we copy the ring data and set out a shadow ring. Finally, we update the IOMU to point the device to the shadow ring, while restore the EPT mapping to the native available ring. This entire process takes around 10 microseconds and is fully transparent to the guest OS. When I/O pressure increases, the device needs to switch back from snooping mode to full pass-through. To prepare for this transition, the hypervisor proactively brings swapped out page back in memory. Once all the required pages are confirmed to be present, the mode switching is complete simply by remapping the IOMU to point back to the native ring buffer. This allows the device to resume direct access with no additional overhead. In our production test, the mode switching adds a small delay, about 200 million seconds, similar to Cumul Live upgrade, but overall it works smoothly. To further reduce the number of page faults, we add a mechanism called lock page. With IOPS snoop, we can track which pages are accessed frequently. This hard page can be selectively pinged. The figure on the right shows the distribution of the log page rates across VMs in production. At P90, the log page rate is around 10%, which means that for most VMs, locking in just 10% of the page is enough to effectively reduce the occurrence of I/O page faults. However, at P99, the log page rate increased significantly. This spike is mainly caused by a small number of Windows VMs whose virtual drivers exhibit poor I/O locality. As a result, this VM requires many more pages to be locked, which push up the overall P99 value. For more technical detail about our work, please feel free to refer to our paper. We evaluate VIO extensively in Alibaba's cloud. The baseline we compare against was VPRI, a hardware-based solution using DPU support. One of key measurements we made was the cost of a single IOPS snoop operation. When a page has already been locked by our lock page mechanism, the snoop takes only 3.5 microseconds. If the page is present in memory but not locked, it takes slightly longer, about 4.5 microseconds. But in the worst case, when the page has been swapped out, resolving the fault takes around 700 microseconds. The important point is that all of this happens before the DMA starts, so the data transfer is never interrupted. This is very different from hardware solution like VPRI, which handle page fault during DMA transfer. They rely on upper layer protocol like TCP RDMA retransmission to recover from failed transfers, which introduce performance jitters and can hurt tail latency under pressure. You can see this clearly in the figures on the right. It shows the results from an iPerf test. When I/O pages fault occur, VPI exhibits noticeable performance spikes, while VIO remains smooth and stable throughout the test. Our application-level benchmark confirms this difference. Under ideal fault-free condition, VIO snooping mode does introduce some overhead compared to hardware pass-through. However, as soon as page faults start to occur, VPI's performance degrades sharply, while VIO stays stable and predictable. To summarize, VIO is a full software-based solution built on a VertIO interface. It enables pass-through I/O without static memory pinning, supports legacy VMs without gas or hardware change, and has been widely deployed in Alibaba Cloud production. Thank you for your attention. I'm happy to take any question.